Hey everybody, it's Mr. Clausen here. Just want to run through how to generate a velocity versus time graph with you. So to get started, what I would like us to do is just to review what we already know. So there we are. Our essential question for today, how do I create a velocity versus time graph? And we're reviewing what we know. So what we know so far is that the slope on a position versus time graph tells you the object's velocity. If that slope happens to be a straight line, which is what I tried to draw there with my finger, but got a little wavy, is that tells us that it has a constant velocity because a straight line would have a constant slope, and since slope equals velocity, straight line, constant slope, constant velocity. Okay, now we say velocity as opposed to speed because speed you can get from the slope of the line. So if you take a look down here, it says speed is the magnitude of the slope, or the absolute value of the slope is the speed. And so yes, the steeper the line, the faster the object will be going, but we talk about how velocity is important on a velocity versus time graph. Because if the slope is positive, it means it's moving in the positive direction, and if the slope is negative, it means it's moving in the negative direction. So like I said, these are things we already know. We're just going through the review. The last thing we wanted to take a look at is how the y-intercept is important to us. And if we take a look here, the y-intercept shows us the starting position of the object, which can sometimes be beneficial or needs to be taken into account when we're doing problems. So as long as we got that, now what we can do is start working on how to actually create a velocity versus time graph now that we understand our position versus time graphs. Okay, so flip over to the other side of your notebook right now. What you need to do is set up a couple different columns. So you should be on the left-hand page now if you're following along at home. And set up a position versus time column and a velocity versus time column. Now we're going to have 4 scenarios in whole. So go ahead and get that set up if you need to. Key things to note here with the velocity versus time is you'll notice that the shape's a little different. We have 0 in the middle, and what we're going to be doing is we're going to be traveling in the positive and negative direction for the velocity versus time graph. So just be sure to set it up in this T shape here as you go. So pause the video when you need to get down what you have to, and then hit start when you're ready to get going again. All right, so the first thing we're going to need to do is we're going to need to set up a position versus time graph for the scenario that we have listed up here. So it goes 8 meters in 4 seconds. So what would that look like? Well, the position versus time graph, I should have labeled the units, but I forgot. So I put meters on there, and then I'm going to put seconds over here. So to get a position versus time graph for something that goes 8 meters, you just somewhere near the top write 8 meters, and then somewhere along over here on the side you'd write 4 seconds. Now we know that that object is going to travel those 8 meters in those 4 seconds, and so its location or its position would be located about there. Since the object is traveling at a constant velocity, we know that it would be traveling with a straight line, and it said it started at 0. Okay, so there we go. Now how do we go about getting a velocity versus time graph from this? Well, that's just what it is. It's a velocity of the object. So how do we calculate the velocity of an object? We know that it's equal to the slope on a position versus time graph. So in this case, the slope would be equal to the change in the position, okay, delta x, over the time interval, or the change in the y, or excuse me, over the change in the x direction. So to do that, it's delta x over delta t, and this is how you can calculate velocity. So if we go ahead and we put in our change in position, it started at 0 and it ended at 8. So the change in position would be 0, 8 minus 0, otherwise known as 8 meters. And the amount of time would be 4 seconds minus 0 seconds. And so the change in time would be 4 seconds. And we picked some easy numbers here for us to work with in the beginning. And you'll see that the velocity of this object is 2 meters per second. Now, why is that important? Well, we can use it to help us set up the graph over here. Now, I just want to run through a couple things. What does this mean to say that it travels 2 meters per second? Well, the way to think about this is it means that for every second that the object's traveling, it travels a distance of 2 meters. So if we take a look here, in the first second, how many meters would it have traveled? So if it traveled for 1 second, it would travel a distance of 2 meters. If it travels for another second, so from 1 to 2, how far is its position going to change? Well, that means it's going to travel another 2 meters. Well, if it started at 2 and you go 2 more meters, the total distance it would travel would now be at 4. Okay, and at time of 2 to 3, okay, that's another 1 second interval. How much did its position change by this time? Well, it travels 2 meters every second, so now it's traveling at 6. And the last one is it finally goes 4. Now, why is this important? We drew it this way too, and what you can see is that during each 1 second interval, so for that second 1, second 2, second 3, and second 4, the slope is the same at any point along there, and that will help us out over here when we're trying to calculate the velocity versus time graph. So to set it up, what you would do is you'd go 1 second, 2 seconds, 3 seconds, and 4 seconds. And then what you do is you just list what is the velocity during those times. Well, up here, you would say that the object was traveling 2 meters per second, okay? And at second 1, the slope was 2 meters per second, so its velocity was that. At second number 2, the slope was still 2 meters per second, so the velocity would still be 2 meters per second. At second number 3, hopefully you're finding a pattern here, the slope is still the same 2 meters per second we had before, so the velocity would be right there at 2 meters per second. And then number 4, we have that. Now if you go ahead and put this all together, what you end up getting is a nice straight line, which shouldn't be too surprising to you, considering that this object traveled at a constant velocity, and we would expect that its velocity would remain constant. Okay? So that's scenario number 1. An object goes 8 meters in 4 seconds. All right, let's try another one now. Let's go to the next. Okay, everybody, so let's take a look here at the next scenario. It says we're going to start at 6 meters and go to 0 in 3 seconds. So we go over here on our position versus time. We'd put 6 up near the top, so that's 6 meters. And then down here at the bottom, we know it's going to take 3 seconds for it to get to 0. Now, what would that graph end up looking like? It's going to be a straight line, and it's just going to go down like so. Okay. All right, so there we are. There is our starts at 6 meters and goes to 0 in 3 seconds. Now, how would we figure out the velocity versus time graph? It's going to be set up in much the same way. Velocity is the slope of this line, or you can take a look at it as its change in position divided by time. So in this case, velocity would be the change in position divided by the amount of time that takes place. So we started at 6 and ended at 0. So in this case, you put the second one first, so 0 minus 6 meters. And then divide that by the amount of time it took, which would be 3 seconds minus 0 seconds. And if you put this all together, what you'll end up getting is negative 6 meters over 3 seconds. Okay? Divide that out, and you'll quickly see that now what we have is negative 2 meters per second is our velocity. Now, what we could do is for over here on our velocity versus time graph, this time you'll notice that it's negative, so we've got to go down here. We put in a negative 2, and we'll put meters per second for our unit. Okay, so negative 2. Now, once again, just like before, what we have here is it doesn't matter at where we look at this on our velocity or our position versus time graph, the slope is always the same, this same negative 2 meters per second. So at any time during that interval, those 3 seconds, it's always going a negative 2 meters per second. So what we end up getting is a straight line right there. Okay, so that's how the velocity versus time graph would look for that one. Now what we'll do is we'll take a look now here at the next scenario. Okay, for this next scenario here, what I'd like you to do is I'll give you a position versus time graph, and I'd like you to come up with the velocity versus time graph. So we'll try this again. Top should be in meters, and the bottom should be in seconds. All right. From this, hopefully what we can get going on is what I want you to do is I want you to label your axes as so. Put 6 meters up here at the top, 3 would be in the middle, and then 2 would be just below it a little bit here. All right, so the object's going to start at 3 meters. It's going to travel down to 2 meters, so we'd have a straight line right there. And it's going to take 1 second to do that. From that point on, it's then going to take 4 more seconds, so the total time would be 5 seconds, and it's going to travel out to a distance of 6 meters. Okay? So from that information, what I'd like you to do is I'd like you to figure out what you think the velocity versus time graph would look like. So go ahead, hit pause, and then we'll come back and take a look at this in just a moment. All right, hopefully you had time to figure it out. And this is how we would go about doing it. So the way to do this sort of a graph is when you have 2 different slopes is you're just going to have 2 different velocities. So we just go ahead and split it there. And what we do is we just calculate the velocities independently. So let's do here the slope for this first portion. So from 0 to 1 second. How we'd calculate that out is, once again, it's just change in position divided by total time. And so in this case, the position goes from 3 to 2. So it's 2 minus 3 over 1 minus 0, because we had 1 second go on. And so what we have here is -1 meter in 1 second, otherwise known as a velocity of -1 meter per second. Okay, so for that first time interval, for that 1 second, the velocity would end up being -1. Okay, and during that whole time, that's how fast the object was going. Okay, now at the 1 second, the object changes direction, starts going the other way. So then what we have to do is we have to take a look at what is the slope during this next interval. Okay, so let's take a look at the change in position for that second part. How we would do that is we would go change in position divided by time. So the position was 2 and then ended at 6. So we'd write 6 meters minus 2 meters. That's going to be 4 meters. And we divide that by the time interval. Well, the time was 5 seconds when we ended, but we started at 1 second. And if you subtract that off, what you end up getting is 4 seconds. So while these graphs look differently, as soon as you do the math, you can see here that the velocity for the second interval was, not negative, I don't know why I put that in there, disregard. It is just 1 meter per second, but this time it's in the positive direction. So we come up from here, so for second 1 to second 5 on our velocity versus time graph, we have to end up coming up about the same distance, and we write 1 in for that. Okay, and what that means is during every one of those intervals, remember the slope stays the same, so for all those seconds, the velocity was at 1 meter per second, and what you end up getting is a line that looks like this. Now, what's common to do on velocity versus time graphs, since you see that we just have these two horizontal lines, is it's very common to just draw a line on them to kind of box them in. And then what we do to make sure that we can see what's going on is we just shade in that box right there. Okay? And so this is what the velocity versus time graph would look like for the graph we had over on the other side. Do the same thing. I'm going to give you one more scenario. I want you to figure it out, and then we'll come back and take a look at it. All right, here's our last scenario we're going to do here. So we go down to our last graph, and what I want us to do, it's going to be a very simple position versus time graph. The two time intervals we're concerned with is 3 seconds and out at 9 seconds. And the only position we need to put on our position axes is going to be 3 meters. Okay, so what happens here is the object is going to travel from 0 to 3 meters, and it's going to take 3 seconds to do that. And then it's just going to stand still for 9 seconds. Okay, what would and stand still until 9 seconds. What would the velocity versus time graph look like in this situation? So go ahead, pause the video, see if you can come up with it, and then we'll come back. All right, so what we would do here is for the velocity versus time graph, we do the same thing we did before, break the graph up into different sections. So if you take a look, there's a nice break point there at 3 seconds. We can see what's happening is that the object is moving and then it's standing still. And we just figure out the slopes for each one of those. Now the first one's pretty simple, change in position divided by change in time. We have an object that travels 3 meters and it takes 3 seconds to do that, so it has a velocity of 1 meter per second. So if we go over for the first 3 seconds, it was constantly traveling at 1 meter per second. So on our velocity versus time graph, we put in 3, and then we just come up here to positive 1, and we draw a horizontal line. Okay, now what happened at the next part? It's not as hard as you think. What's the slope of this flat line? Well, that's the key right there. It's a flat line, so the slope is 0. So what would be the velocity at this point? It would be 0 meters per second. So how do we indicate that here on our velocity versus time graph? We do just that. We just put the line and we just darken it in a little bit, and we just show that it had no velocity for 9 seconds. Okay, so that's how we do those scenarios. Now what I want us to do is we're going to go back and we're going to take a look and see if there's some more information we can find from this. And there is, so let's just go back up to the beginning. I'm just going to need a new slide to get things reset. Okay, so I'm back up here at scenario number 1, and what I wanted to take a look at is what is the actual displacement of the object. So if you take a look over here, it's easy to see that the displacement goes from 0 to 8, okay? But if you take a look at a velocity versus time graph, there's a way to get that the displacement was 8 as well. And if we go back and we do that thing where I said typically what we do is we just kind of shade in on a velocity versus time graph between the line and the axes, there's a way to get the displacement here as well, and it works out pretty well. What shape is this? Hopefully you're going to say that's a rectangle. And if I were to ask you, how do you calculate area? You'd say, well, area is length times width. Well, in this case, take a look at our rectangle. It's a rectangle that has a length of 4, happens to be 4 seconds, okay? And it has a width, you could say, or height of 2 meters per second. Now what happens if you take and you multiply those two things together? Well, the 4 times the 2 gives us 8. And now if we take a look at the units, we have seconds times meters per second. And so what happens with the seconds? Those cancel out, leaving us with just meters. Now once again, what did we say the displacement was over here? Well, we said the displacement over here was going to be 8 meters. And if we take a look over here, what did the area on a velocity versus time graph tell us? Well, it told us that it was also 8 meters. And so what we're starting to think here is that the area of a position versus time graph is equal to the object's displacement. Okay. Now, that might have just been one nicely picked example. Let's take a look to see if it holds true in some of our other ones. All right, so here's problem number 2. Let's take a look at what this displacement would be. Well, the object started at 6 meters and it went to 0. So the displacement would be negative 6 meters. Well, let's take a look at over here if we can figure out what this would be. This object went out to 3 seconds. So if we shade that in, okay, if you were to find the area of this graph, what you would have is, let's just start with over here, this is negative 2 meters per second, and we would multiply that by 3 seconds. Once again, the seconds cancel out, and negative 2 times 3 is negative 6 meters. So what we just confirmed here is that the area under a velocity versus time graph is the displacement of the object. Well, let's try the next one, see if this really holds true, because this one might be a little bit different. If you take a look here, this object started at 3, went to 2, but we don't include that when we're talking about displacement. Really, it just started at 3 and ended at 6. So the total displacement for this object, according to the position versus time graph, it has a displacement of positive 3 meters. How do we get that if you take a look over here? All right, so how we would do this is we just take a look at both areas individually. What would be the area underneath of this little box? Well, it's a negative 1 meters per second times 1 second. So that would give us a displacement of negative 1 meter. Okay, let's take a look at the area of the top box. The top box has a length of 4, so do note that it does say 5, but it started at 1, so the area here is actually, or the length here is actually 4. So we would have 1 meter per second times 4 seconds, which would give us a displacement of 4 meters. Now, if you add those two boxes together, what do you end up getting? Well, 4 meters plus negative 1 meter gives us a total displacement of 3 meters in the positive direction. So what we're finding out here is that the area of a position of a velocity versus time graph, the area between the line and the axes, so wherever the line is back to the axes, that area represents the displacement of the object. So we no longer need to use the position versus time graph always to get there. We can get the information just from the velocity versus time graph. So what I'd like you to do now is I'd just like you to copy down a couple notes so that we can get this down to make sure for what we actually learned. All right, so a velocity versus time graph, what do you need to know about that? All right, on a velocity versus time graph, all right, we'll set it up like so. Here we are. If the object was a flat horizontal line and it looks like this, this means the object was traveling with a constant positive velocity. Okay. Sound good? We could call that maybe forward. Now what it can do is if it turns around and goes the other direction, the velocity versus time graph would look something like so. And we shade in between that and the axes. And so this would be a constant negative velocity. If the object is standing still or has no velocity, you just put it at right there. So this would represent 0 meters per second. Okay? The other thing we want to take a look here at a velocity versus time graph is the neat little shortcut here on how to find displacement. Is we found out that on a velocity versus time graph, all right, if you take a look at the area of that curve, what you're actually going to get is the object's displacement. And the neat little trick for how this works is you end up taking the object's velocity and you multiply it by the time, and that'll give you the units of meters, which is what we need for displacement. So the area between the velocity versus time graph and the axis, that is equal to the object's displacement. If you have any questions, come see me in class.